Good afternoon, everyone. Welcome to the new season of Tah Poe Seminar. And our first talk is given by Dr. Ninnat, Dangniam, and his topic is Fermion Sampling, a robust quantum advantage game with fermionic linear optics and magic states. So, and the audience on site and online, please feel free to ask questions. So let's welcome him.
Yeah. Thank you for introduction. Okay, so yeah, let's get started here. So I was asked to. It's a good time to give this talk because this is just recently published in PRX Quantum this year. So this is a joint work with Michał Ośmaniak at Warsaw, Poland. Most of the work is done when I was a postdoc, sort of remotely there. And Mauro Morales, now a PhD student at University of Technology, Sydney, and Zoltan Simburas at the Wigner Institute of Theoretical Physics, I think, in Hungary. Okay, so I have given this talk a few times, and it was mostly to advertise my paper at conference and to experts and stuff. But well, today I will give a bit of a different style of talk. So because I know that most of you in the room are not familiar with this topic of quantum, sort of like quantum computing research. So let's first start by, well, defining sort of the main question that we are interested in. Okay, so this is the outline of the talk. I will so first is the introduction of what is a simulation of a random process, basically. And then I will introduce the so-called fermionic linear optics, which is the mysterious thing in the title of the talk and the paper. And then I will sort of briefly go through the main idea of this proof of quantum advantage thing, and then a summary. Okay, so when you think of simulation problems, maybe some people think of the matrix. It's like, is our universe simulated or not, or the aliens or something, or whether robots can or artificial intelligence can simulate real intelligence. But I will focus on a boring problem, which I would actually claim that is actually very interesting, and it's sort of an abstract idea of simulation. So just to agree on the terminology, we have basically, here first we have a classical circuit. You can think of it as a Boolean circuit or something. Then you input some bit string. So I will denote bit string by this boldface X. And this symbol is just mean it takes value 0 or 1, and there are n copies of them. These are examples of bit strings. And then suppose that this Boolean function actually is probabilistic, so it's some sort of randomized algorithm. It just spit out, well, it lets you, when you see the result, you see some bit string, but at different time that you run, you see some different bit string according to some sort of this probability distributions that is determined by this sort of black box function f. And the question then is, well, what does it mean to simulate a random process or something like this? And I mean, this can be something very general, or for example, I don't know which year, but for example, Francis Galton developed this idea of the so-called Galton board to sort of simulate the normal distributions. This is just, you can make this out of wood or something, and then there's a text everywhere. There's a bin that when you throw in the marble from the top, then it will sort of bounce randomly along some trajectory, and that it will land on one of the bin. And then by statistical nature, if you do this a lot of time enough, you get, well, there's not a picture here, but you get that the distribution of the marble will be close to normal or Gaussian distributions. But then you can think of like different ways of simulating things, right? So if you have a random process, maybe you can ask whether you can, so here what the Gaussian board does is that it's sort of let you sample from the distribution, from the binomial or Gaussian distributions. But maybe you can ask, well, what is the probability distributions that the marble will be in one of the slot here, or here, or here, or you can ask like at different time slices, right? Or you can just ask at the end, which is, well, the question, what is the probability distribution, is actually different from asking, well, how you can produce a sample, right? Because if you want to produce a sample, then you just throw in a marble, and then just give you one sample. But if you want to calculate the probability distributions, basically you have to build up enough samples to see the histogram, basically. And you know, the larger number of samples you see the distribution more accurately, but you're never guaranteed to see like the exact distribution. Okay, so this leads to basically broadly two classes of simulation of random process, which actually in the literature called weak and strong simulation. And thinking back to compared to the previous slides, so I would call the ability to compute the probability itself a strong simulation, and the ability to sample from the distribution, the weak simulation. And there are reasons why it's called weak and strong. And when you want to be precise, there also need to be some notions of errors, or if it's zero error, is it exact strong or weak simulations. For example, I can say here that let's say that when I say strong simulation, I mean that for the target distribution P, I want to calculate something or produce an estimator Q for, say, each bit string X, such that the error here is bounded by some constant times the probability. This is the so-called relative error model. It's I think it's kind of popular in like proof in computer science, even though maybe you ask what is the meaning of this. It looks kind of weird, and actually it's a very stringent notion of errors, right? For example, if the target probability Px for some x is except x0, then you need to be able to compute this approximation. Well, it's not approximation anymore. You need to compute Q exactly, precisely, right? So if this Px is 0. Or maybe you can have an so-called additive error as well, if this right-hand side is just a constant. But this will be the definition of strong simulation that I will always use in this talk, unless stated otherwise. On the other hand, for weak simulation, I will use this notion of weak simulation, or like approximate sampling up to an additive error. So this epsilon will just be a constant, and you can already see some more difference that, well, this on this side, the total the error budget depends on all of the bit string, all of the points of the distributions. Whereas in this here, I can just point to each x is this string and then say, okay, maybe I want you to compute p for this x, maybe for that x, and so on. And actually, as I maybe alluded a little bit to, there are many different notions of error that you can put in. And but if you say change the notion of errors for strong and weak simulation, then some of the things that I will say may not be true, for example. Okay, now we can talk about simulation of quantum circuit. So on the left here is the classical circuit that I just show in the first slide, just some logical Boolean circuit. And here for quantum circuit, now you just change everything to a quantum state. The circuit becomes some unitary operator, and then maybe you measure the poly Z at the end. And whereas each line of this is one qubit or two-level systems. And you can think of when you compose different lines as tensor product. Right? So for example, the state over here is just 0, tensor, and so on. So now before we go into talk about quantum advantage, we have to say a bit about the difficulty or hardness of simulations of, well, the hardness of simulation of classical random process and quantum random process basically is like coherent process. So actually strong simulation, well, it's sort of obvious that weak simulation of this kind of thing is easy on their respective hardware. For example, on the left, if you could build a classical circuit that does what F does, then it will obviously let you sample from whatever distribution it is. So that constitute a weak simulation. But the strong simulation is actually pretty hard. It's actually harder than NP. So NP is some problem that basically we have, we currently believe that we have no hope of solving if the size of problem increase, because the difficulty basically increased exponentially with the size of the problems. And this is even a little bit harder. So you can sort of see that the notion of strong simulation is actually kind of weird, even though it's maybe a notion of simulation that maybe come to your mind first, that, oh, I want to simulate random process, why don't I calculate all the probability distributions? But it's actually very hard. I mean, even with n bit here, the outcome is, the set of possible outcome is 2 to the n bit string, right? So even writing down the result for each value is going to be difficult if you have a lot of bits, if n is large. And actually, sort of similarly, but also a bit different, is that, well, first of all, weak simulation, if you have a quantum computer that implement this unitary, then weak simulation is again easy. But strong simulation is actually very hard. It's much harder than NP. There's sort of an infinite hierarchy of hardness over NP, and this thing is above all the infinite hierarchy. It's extremely hard, and we also don't believe that quantum computers can even calculate this. Whereas, oh right, I forgot to mention. So of course, if you have quantum computers, then you can really simulate it. But actually, this is also basically a class of problem that you can use to define a quantum computer, or like problems that quantum computer or quantum device can solve. Basically, because if you think about it, even if you want, suppose that you want to run Shor's algorithm to factorize integers, or some optimization algorithm, or some quantum algorithms, at the end of the day, basically you just run this huge unitary and then you sample the outcome from the result. Like that's the only thing that we ever do at the end of the experiment. And say if you're running Shor's algorithm to factorize integer, now the outcome that you get has the meaning, right? Because it's correlate back to the problem that you put in. It's like it should tells you, for example, tell you about integer factor of some integer that you put in as an input of the circuits. But if you abstract away all the like specific of the problem, all that you ever do is actually sample, actually make the measurement at the end. Right? So this is a class very natural for quantum computers. And actually this is the sort of thing that people propose as the so-called quantum advantage scheme. So you pick basically a set of quantum circuits, or maybe all of them, you allow you to be anything, or maybe you just choose a smaller set, and then you say, okay, if you have a quantum device that is good enough, not too noisy, then you can just run device and make a measurement at the end. And up to some mathematical proof that theorists have to provide, this should be very hard. This weak simulation of this thing on a classical computer should be really hard. And that's something that we want to prove. So in 2011, Aronson and Arkhipov, his student, argue in the boson sampling paper that one can prove the hardness of weak simulation of a quantum system on classical computers. So prove that it's hard. You can prove this if if you can prove some version of that strong simulation of these circuit is hard, and you have some property that I haven't told you, like maybe in the second half of the talk, what this means. This property called anti-concentration of the output probabilities of that circuit family. But this is just something you can keep in mind. And actually, just these 2 points, well, this paper is actually like 100 pages long. And yeah, it turns out to be very influential. All the quantum supremacy, quantum advantage scheme that Google does, China does, some private company does, sort of stems from this kind of like proof ideas that, theorists have to prove. And then if theorists say that, oh, the proof is good enough, then experimentalists go and try to replicate this experiment. Okay, this is sort of what I said before, but to be more precise, so what we want to prove is that there's a family of quantum circuits, and if I pick this U at random, so actually random, if you know what that means, then there's a high chance that basically there is no classical computer that can really simulate the outcome of this circuit. Well, maybe you can skip this, but you can, yeah. Any questions so far? Okay, so well, you have realized somehow this talk must have something to do with fermion because it's in the title. But where are the fermions? So basically, the story is that, okay, so there's this quantum supremacy scheme announced by Google in, I think, 2019 on their 53 qubit processor. And what they do there is basically just sampling from a random circuit where the circuit is basically composed of 1 and 2 qubit gates where then you can pick at random. But actually, interestingly, the kind of gates that that processor can do so is some kind of superconducting qubits like Gmon transmon or something. I'm not an experimentalist. But it turns out that there's this peculiar looking sort of gates that they can produce basically really well with high fidelity. And the way you read this is 2-qubit gate, so it's just 4x4 matrices, unitary matrix. And actually so these kind of gates are sort of native to their architecture, and they actually call it FSIM, come from fermionic simulation, which I will say in a minute why. And they can use this processor for many different things, like doing quantum chemistry calculations. So yeah, because you have a lot of fermions in quantum chemistry, and do some approximate optimization algorithms or some other tests. And so it's a very, I don't know, nice, maybe the set of gate that maybe we should pay attention to. And actually, this is sort of a bit of a disparate point that is also related to our work, but I probably won't go into too much detail. So I will just say here that, well, suppose that if not only that you can do these circuits, this case well, but let's say that, okay, maybe what if you want to use only these gates to demonstrate quantum supremacy? What is the upside of it? Well, one is an experimental pros, right? Because you have devices that do this really well. And then there's some more theoretical reason as well that you might want to look into using these circuits. Well, it will not be obvious now, but actually you can learn about this circuit pretty efficiently. And when I say learn, I was thinking about that. Well, when you do this kind of quantum sampling experiment, I say that, well, it's sufficient to just basically run the device, right, to do a weak simulation. But let's say that, okay, so let's say that I want to use that quantum processor and run the distribution and then do the measurement at the end. And then I say that, oh, this experiment is actually, how should I say it? The way is it, can I be sure that this device in the lab actually produce the correct experiment, the thing that I want? Then I would have to do something like this, right? So I have to compare the distributions that I got from the device itself to the ideal distributions that I want. And then say that, oh, it is actually pretty close. But in order to do this, you actually have to do strong simulation because you have to calculate this Q and compare with the ideal distributions. And so actually, that is actually something that these quantum supremacy experiments sort of have to do. They sort of cannot avoid it, even though it's very inefficient. But suppose that I can restrict to gates that have like more structures. Then maybe I can sort of bypass that. Maybe I can make some assumptions and being able to make an sort of indirect certification that my device is performing correctly. So by indirect, I mean not like doing strong simulation of this and then just calculate the difference and then see if it works or not. And actually, it's one of our results that if for this fermionic linear optic circuit, this kind of thing is possible. Okay, so let's look more a bit into this, like the structure of this peculiar structure of the gates. You see immediately that it acts on the even parity and odd parity subspace separately. And that's because the way that I label the qubit state is like 0, 0, 0, 1, 1, 0, 1, 1. So if I have the two values, if the two values are the same, I say it's even parity, right? Actually, it's more than that. It's the thing in the odd parity subspace is just some X rotation, and the other one is Z rotation. So this structure of gates where you have a different two-level unitary. So this U minus and U plus are 2 by 2 unitaries that act on the odd and even subspace respectively, and otherwise is just the same. It's just the same like one qubit, one like spin 1/2 unitary that you can generate from Pauli XYZ. And in that addition, if you have the restriction that the determinant of these two unitaries are the same, then you get something called the match gates or the fermionic linear optic gates. All right, so the restriction here is a bit mystery at this point. But for example, so what kind of thing that this restriction limit us? For example, you cannot do a swap gate. Well, swap gate is not a part of this FLO gates because the swap gate is basically just off diagonal in the 0, 1, 1, 0 subspace, right? So it's swap the 0 and 1, the first qubit and second qubit state, but the determinant of X is -1 and the determinant of the other thing, which is just the identity, is 1. So somehow you cannot do swap on this model. But yeah, the great question is, well, what does this have anything to do with fermions? So actually it's come from something called the Jordan-Wigner transformation. So it's a way to map between spin model, so or here qubits model, to exactly solvable free fermions model. And you first do this mapping by identifying the computational basis state, so the 0, 1 state, with occupation number states. So like the black dot here means particle exists here. And well, there's one student in the, yeah, there's just reminder in case. The Jordan-Wigner map, so in the Jordan-Wigner map, you define this operator from basically a creation operator for a two-level system, and then a bunch of poly Z, a trail of poly Z at the end. So something like if you have a linear chain of qubits, then the creation operator at site J is a qubit creation operator here, and then poly Z, just all the way. And that the trail of Z is just there to satisfy the canonical anti-commutation relations for fermions. All right, so you think of this as creating a fermion at site J. So because at least this creation operators will actually like flip the qubit from like 0 to 1. Or if the Hermitian conjugate of it is the annihilation operators, that's the opposite. So that's sort of one part of connection to fermions, but actually well, if we want to see something more, it's actually more convenient to go into this so-called Majorna basis, which is really just analog to, so in the bosonic case, you have creation and annihilation operators, right? And then you can form a pair of Hermitian operators from them, which is basically just position and momentum. So here you can do this, do this thing, and then you get basically that one of them is a tensor product of a bunch of Z and then X, and then one of them is tensor product of Y and a bunch of Z. And well, why are they called Majornas? Well, people just say that, well, you can think of each of them as a particle, just like there's only one operator is both create and annihilate at the same time. But I would just say it's just like Yeah, it's just some kind of picture that people here have in mind, so that they call this Majoranas. But now if you define it like this, and then so there's a X Majorana and Y Majorana, right? And then I combine the index, the double index into just one. So the J that labels the site and then X or Y, then I can write an sort of a compact canonical anti-commutation relation without having to like separate relation between like F dagger and F. And actually you can just, well, if there's a student here taking quantum field theory, you can compare it to Dirac gamma metric, where in that case, the delta here, which is the Euclidean metric, will become the Lorentzian metric instead. So then now I can define the Hamiltonians and unitary that correspond to FLO. So these are the guys that are quadratic in, well, either the Majoranas or the creation annihilation fermionic operators. There are some peculiar way that I write here, but maybe you can just ignore for a minute. But physically, so what does these Hamiltonians actually look like? So the way I draw a picture here is I imagine splitting a fermion, right, or a qubit or an electrons into X and Y Majoranas. And then if you multiply, so quadratic, you multiply two of them. And here is sort of the graphical way that I draw the resulting operators that you get from having quadratic Majorana at adjacent sites. So you can do single Z at each site, or you can do entangled gate XX or YY or YX or XY. And what happens if you multiply Majorana from different sides together from non-adjacent side? Well, then something else happened, but it turns out that despite the fact that I said that swap gate is not part of FLO, there's something called I swap. So this is not exactly swap because there's psi there to compensate for the determinant. But what this does in the fermion picture is that it swaps modes, different modes of fermions. But it corresponds to something a bit different in the circuit in the Hilbert space picture in here. So you can do this I swap and then put them adjacent again. So here, interestingly, so if you look at swap gate, so what does not present here is actually the ZZ interaction. So the FLO doesn't allow you to make an isotropic, like 3D isotropic interaction. Okay, let's see. All right. So the form of Hamiltonian here, well, I just write it in this way just for convenience, because of the anti-commutation relation. If I swap M alpha and M beta, then I sort of just get the same thing in the commutator. But we know that commutator is anti-Hermitian, so I have to put I here for it to be a Hamiltonian. And actually, very importantly, it turns out that because of this swapping shenanigan, that this bilinear form or quadratic form that you put here, and the label of it, I sort of write suggestively to like for you to sort of see it as a matrix element. This has to be anti-symmetric just because of the anti-commutation relation there. Then now I can define the unitary, the FLO unitary to just be, the exponentiation of that Hamiltonian, right? And it can be shown, so like we are trying to characterize, to see what exactly this FLO thing is. It turns out that if you sort of put all the 2n Majorana operators and stack them in a row, and then you just write as a vector, and then you conjugated by the FLO unitary. So this is like a Heisenberg operator evolution, and do it every element-wise. It turns out that this is just a rotation of this 2n long vector in 2n dimension, just real space. And we know this because, well, you have to derive the last equality, but we know this because the matrix H that I just showed last slide, I said that it's anti-symmetric. Then when you see this form, you can see immediately that, oh, if you have an anti-symmetric like real generator, it generates rotations, right? So this is actually a generator of 2n dimensional rotations, and actually is a defining representation of the group SO2n. So very interestingly, if you have n qubits or n modes of fermions, all unitary evolution that are physically allowed is very big. It's a unitary group of 2 to the n dimension. But this FLO operation is really just a tiny rotation group inside here, just something in 2n dimension instead of 2 to the n. And maybe I won't go into too much detail here, but you can sort of see that, well, it's not approved, but the last slide sort of suggests that if you have sort of the right state or the wrong state, that depends on what you think is good or bad. If you have a state that sort of lies in here, then and apply FLO unitary, then it won't go very far. You won't be able to travel to a lot of places in the Hilbert space. And that is actually true, that if you start with this all zero state, well, I don't want to focus too much on the derivation, but with some kind of tricks, some kind of like doing weird things, you can sort of write this as like a Gaussian operators, kind of like the thermal density operators, where the density matrix is an exponential of something that is quadratic again in the fermionic operators. And therefore, if you know the transformation of a linear fermion operators, then this transformation also induces the transformation of the quadratic fermion operator, right? Because you can just put V and V dagger here, and then write, and then pop in V dagger V over here as the identity. And actually, this is the adjoint representation of SO2n. But why do I tell you all of this? So the upshot of it is that this kind of, or basically simulation, even strong simulation of fermionic of FLO circuits, starting from this all zero computational basis state, is actually very easy, because instead of the curse of Hilbert space, where the dimension of Hilbert space increase exponentially in the number of qubits, here all the calculation you can do, including calculating the probability of measurement at the end, you can do on 2n by 2n matrices instead of 2 to the n by 2 to the n matrices. Okay, so that's what I said. But this sounds like a bad thing for our work, right? Because we want to, well, we ask the question, well, can I show that, can I give a quantum advantage scheme using this fermionic linear optics thing? And well, to be able to have quantum advantage, meaning that, well, to have quantum advantage, you have to show that classical computers cannot simulate or emulate this kind of thing. But I just say that, well, if you have FLO, then everything is easy. But it turns out that there's a way out, and also sort of a lot of evidence is well known that if you change the input state to, okay, so this kind of entangled state, there's a reason it has to be 4 qubits and cannot be less than 4. But yeah, this for another thing. If you can input these states, this entangled state, instead of the computational basis input state, some call it magic input state, then actually strong simulation of this circuit is actually as hard as strong simulation of any other quantum circuit. And so that's a good news for us, right? Because if we want to show the weak simulation on a classical computer is hard, then at least we sort of at least want the strong simulation not to be easy, because weak simulation is weaker than strong. But then the rest is, well, our goal is now to show that instead of strong simulation, we want to show that weak simulation is also hard. And that's a big deal. Okay, 20 minutes. Any questions so far? It's just slides for resting your eyes. Okay. So sorry. So this was defined when you were not here. So we were talking mainly about sort of what does it mean to simulate random process. And basically, weak simulation means that I can just sample from the process. So like I put out a random walker and then just look at it at the end where they are, right? This is actually a natural definition of simulation for random process. But there's another definition which sometimes people sort of associate with simulation, which is to actually compute the probability distributions. But in a lot of time, that is something very hard and very different from this kind of thing. So like some Monte Carlo thing, you sort of always do this kind of thing. Yeah, thank you. And our goal is we want to show that using classical computers to produce sample that's close to the sample that you can get from quantum circuits should be hard. Or in short, that classical computer is inferior to quantum computers, because quantum computer you can just run the program, just run the hardware and then just measure it at the end, just produce a sample. Okay, let me have some water. Yeah, just to remind you of our goal there. Okay, so for this kind of proof, and well, as it is written in the outline after this point, it will be about this proof of quantum advantage conjecture. So if you well, if there are more people, or say if someone wants to sleep, then this is the point that you go to sleep. Okay, so all this proof of quantum advantage for boson sampling, for Google's random circuit sampling, or our fermion samplings have all the same like game plan. So basically, first you assume that there's a classical computer that can weakly simulate your stuff, and then you prove some result called anti-concentration, and this will allow you to improve a weak simulation to a strong simulation. So if you can produce the sample, then you can calculate the probabilities. But with a very big cache here, this is not something that you can do in real life. Because, well, numerics people will be very happy if this is true in the real world. You just sample thing and then you can just calculate thing exactly, for example. But this is sort of, but this is fine. I just want to clarify that there's nothing sketchy going on here. It just says that if you have some kind of hypothetical machine that computer scientists study, then you can do this. And well, at the end, you sort of see why it's not a big problem. But on a broader point, this is more like a mathematical proof. And, you know, mathematical proof only care that statement of only kind like, oh, it's worthwhile to study statement of the kind like X implies Y, even though X is not modeled by anything in our real world. Right? Because like mathematical universe have many things more than physical universe. But I digress. Okay, so you now have strong simulation, and the rest is you have to prove that this strong simulation is hard. And if that is the case, then it will say some statement that about this hypothetical machine that computer scientists believe to be false. And this was actually like half of my first talk in the beginning of the year, when you don't need to know anything about that. And so contrapositively, so if you go in the other direction, if this conclusion is false, then you can conclude that there does not exist classical computer that can really simulate the thing that you want. Yeah. Okay, so we have to prove these two things. So now, in this 15 minutes, so go quickly just through the main idea, not really the proof. Okay. So first of all, anti-concentration. So the point of introducing anti-concentration here, if you remember from the last slide, is that you sort of want to convert between weak and strong simulation. With this definition of errors that I introduced in the beginning of the talk, here is an additive errors. Well, I didn't write it here, sorry. It's like here, you're supposed to calculate or make an estimate of a probability up to a relative error, which I write here in this slide. And as I mentioned, this thing is a lot more stringent than the right-hand side if the probability P is small, right? As I mentioned, if it's 0, then no matter what the ratio of approximation eta here, you have to compute P exactly. So Q has to be equal to P. Q is the estimate you compute. So well, to relate these two, you sort of want most of the probabilities to be large. And then intuitively, so you may sort of imagine something like this where you have, okay, so this is the X axis is the bit string, and then the Y axis is the probability, right? And then I just sort of draw some random histogram of probability, and the area under the curve has to be 1 because probability is normalized, something like that. And if I want most of the probability to be large, I can imagine that there's some line here, and most of the probability I want to be above this line. So for example, if you have a uniform distribution, because there are 2 to the n bit strings, all of the probability will be equal to 1 over 2 to the n, right? So everything is on the line, and that's okay. But here, more generally, I just want the probabilities, the outcome probability of the circuits here to be larger than some value most of the time. So the enclosing probability is correspond to the statement most of the time. So there's a non-zero lower bound here that there's a chance that I see big probabilities. And so this is a bit, when you work with something like this, it's a bit puzzling because there's a lot of probabilities that are popping up. And actually to define anti-concentration, so it turns out that, well, so I want to define anti-concentration to mean some statement like this. But how do we arrive at some statement like this? So actually there's a very nice characterization from a paper that I think published after our work. So so when we were doing this work, there's already a definition of anti-concentration, but it's not very enlightening. So it's basically like this, but there's a bunch of like different constant and product and like plus and minus over here. It's kind of hard to say what it means, but an easier definition, I think, is it turns out that anti-concentration depends solely on the second moment of the property. So it's sort of limit how far the variance of is like if you so like how different each probability can be. And so you can define something like this. So you just take probability square and then average over the outcome and average over the unitary. And then the distribution will anti-concentrate if this is bounded away from some value like this. Well, and why is that? So actually this value without the alpha is the value for the uniform distributions. So if you have a uniform distribution, this average over second moment will always be 1/2 to the n. And actually the distance here, so the difference between this value and the uniform value, so actually anti-concentration basically tell you the L2 distance of your distribution from uniform distributions. So if it's 0, then you got exactly uniform distribution. So it's very, very not concentrate, right? It's very spread out, but you can have other distribution as well. And this sort of compact definitions also implies this kind of intuitive definition by something called the Pauli-Sigmund inequality. I know probably physicists maybe never see this, but if you go to, if you want to prove some inequality like this, and you go to Wikipedia, Pauli-Sigmund is the only thing that has the right direction of the inequality, so you use that. And the point of anti-concentration is basically, as I mentioned, it sort of restricts you to your distribution to be close to the uniform distributions. So for example, if I plot the frequency of output probability, so it's like a probability of probability, so it's like probability that I will see this particular value of outcome probability appears. For uniform, everything is 1/2 to the n, right? So it's just peak here. For every bit string, you only see this value of probability. But then it turns out that you have randomness in your quantum circuits. You actually not got something that perfectly uniform out. You sort of got some exponentially falling distribution like this. And this thing anti-concentrate. So this is what we want. But suppose that you have some small amount of randomness. First of all, I think this plot is closely related to something like instead of varying over all possible unitary, you just do a random single qubit unitary at each qubit. So just 2 by 2, just random unitary. Then you get something that's a little bit random, but clearly, well, from the plot, not clearly, but from the value of this value Z is clearly not anti-concentrate because the value of Z is differ from 1 over 2 to the n by a lot. So there's a factor that depends on the power to the n here. So so anti-concentration, to summarize anti-concentration, we want it because we want most of the properties to be large in order to relate relative error, strong and weak simulation in the proof. And the definition of anti-concentration is sort of made so that it's distinguished between these two cases of like a lot of randomness and not much randomness. I don't have time to go into here, but I just want to mention, so those things are just techniques that previous work also do, right? But in our work, so what do we do here? So FLO, I told you, is basically SO2n is a representation of SO2n group in the Hilbert space of quantum states. So you can actually utilize a lot of group theory. So in the previous slides, when I want to calculate to satisfy the condition of anti-concentration, I have to look at something like this, right? So it's you average p square over all circuits, where V here, I mean the VFLO is the fermionic linear optic circuit. And you can just express this using postulates of quantum mechanics, and then use maybe some cyclicity of trace and linearity of trace to pull in the integral and so on. But the point is that in the end, you get something like this. Is an average of some object in an irreducible representation of O2n, so just spinor space that we are working on, spinor Hilbert space. And then you average over it, over like all unitary on this group on both sides. And then everything has this square here because of it's a second moment. So this is some kind of object in the tensor product representation. And under some nice conditions that you can check, if you're lucky, then this is basically just projectors onto earribs, and you can calculate this exactly and so on. And so that's sort of the thing that we did in the paper. Now the other elephant in the room, which maybe I have 3 minutes. Okay. Okay, so the other thing that we want in the proof here, right, is to prove that strong simulation of the circuit is hard. So let's see if I can say this idea sort of quickly in some compact sentence. So basically, you want to. The idea is called the worst to average case reduction. And in computer science, reductions like A to B reductions mean that, so you reduce a problem A to a problem B means that if you can solve problem B, then you can solve A. Like, does that make sense? I think the sentence makes sense. That basically you can write problem A in the form of problem B, then you can use solution of B to solve A. So here, worst to average case has a specific, so average here has a specific meaning that this say that what we want to prove is that if you can learn the value of the property, the output property, or doing strong simulation of like the property of a lot of circuits in the family, then you can do a strong simulation of the circuit that is like the hardest in the family. And this is sort of important because in computer science, when people say some problem is NP hard or sharp P hard or so on, extremely hard, they only mean worst case. If there's one case that's hard, even though like every other case is easy, they still say that this general problem is NP hard, sharp P hard. So this average case is something that we want, because it says that, well, maybe a priori we only know that there's a worst case hard, but if you can do this reduction and you can compute P for a bunch of circuits that you don't know whether it's hard or not, then you can actually, from those value of P that you compute the P for the worst case, which should be the hardness. And so it's a sort of a robustness in the proof of, in the hardness of the problems. That is, there's not like isolate cases that are really hard to find, that are extremely hard, but maybe other cases are easy. Here, if you can prove something like this, you can say with confidence that most of the cases are hard. Okay, I'm not going to go into a lot of details here, but from that key idea there, basically a kind of technique has been developed, I think first in classical computation, to prove this kind of worst to average case reduction. And the idea is some kind of polynomial interpolation. And so roughly speaking, I think that the idea behind this, there's something more, maybe I cannot explain completely, but I think the figure is might be kind of intuitive. So you want to extrapolate from probability of the worst case circuit. So this is probability that you know, well, maybe you don't know which circuit produces this probability, but it exists because you have proved that it's choppy hard or whatever. And then from this value of probability, you want to construct some polynomial that related to the probability of other circuits, right? So then when you do experiments, you randomize some circuit and then you do some sampling. So then you get like several points of, keep building up several points of these probabilities on this polynomial. And then by using some kind of polynomial interpolation technique, so it's basically some techniques in error correction where you only have to sample some number of points on polynomials up to the degree of the polynomials, then there's a procedure for you to recover the whole polynomial. So that in particular, you can just, then once you have the whole polynomial, you can just plug in the value, evaluate the polynomial at the value at that the probability is the hardest to compute to get that value of probability. To summarize, you have to have some kind of interpolation between some probability that you can calculate in some random experiment to the probability in theory that is hardest to calculate, which maybe exists in theory, but maybe you don't know which circuit it is. And well, I just go through this quickly. I think this is like the last 3 slides or something, just to give you a glimpse of an idea of sort of how interpolation actually works. So the first idea, okay, so basically I have to give credits to, so Adam Bolans and Mowasak were the first to sort of import these techniques to random circuit sampling. And the first thing they try is, well, how can you extrapolate between unitary by some kind of polynomial? Well, in the end, you want extrapolation of outcome probabilities, right? But for simplicity, let's not go there. You can first start by interpolating 2 unitaries. And then you can, at the end, you can do like sandwich bracket to get probability, right? Yeah, so the first thing about interpolation between 2 unitaries, so you can define this sort of deformed unitary is deformed by parameter theta, where start at U0, and then you evolve by some Hamiltonian and just multiply it, right? So if the theta is 0, then you have U0. If it's some other value, then just go along some place. But crucially, the error recovery procedure that I mentioned in the last slide depends on the degree of the polynomials. So you want the degree of the polynomial to be low. And so what they did is they truncate this Taylor series for unitary to get low degree. But well, the problem is that if you truncate this, it's not unitary anymore. It's just a fly off from the Hilbert space. But actually, the better idea is to use a so-called Cayley map. So it's a way to map Hermitian operators to unitary operator, but not by exponentiation, with this kind of some like rational functions. And then you can sort of like generalize the polynomial interpolation to kind of like rational function interpolation, and then do the job. Very nice. It has like some nice group theory calculation over here. All right. Okay, we're coming to the end. So yeah, so after we have done that, so we can prove, okay, so let me back up a step. So I mentioned that in the proof of of quantum advantage, you mainly need to kind of I don't know, sub-proof of argument, right? One is anti-concentrations, and one is average case hardness. That like strong simulation is hard, and so on and so forth. So this is sort of so I just picked these three quantum advantage scheme just because the two of them is popular, and the third one is just my work, just to compare. And you can compare them. So something called robustness here is basically the error that you are allowed to make when you sample from those polynomial points. Yes, maybe something that I didn't emphasize here. So maybe the red polynomial is something that you want to recover. But when you sample, you get something like the value on the blue polynomial instead. So there's some error here. And so like the distance here that you can tolerate is I would call it the robustness. And this is sort of the value that people care. Boson sampling has the best robustness, meaning that yeah, you can have a lot of error and maybe still achieve quantum supremacy. And there's yeah, and then there's this. This is a bit worse. Ours is then a little bit worse. But for boson sampling, I think up to current date, well, I haven't checked paper today, but nobody knows how to prove anti-concentration in boson sampling. Whereas in random circuit sampling, actually it's very easy because anti-concentration only depends on the second moments. And if you allow your random circuit to be anything, then you basically choose a convenient set of circuit that almost like automatically satisfy this. You don't have to prove anything. But then it turns out for fermion samplings, or more specifically the FLO gates, it's not random enough. It's not uniform in the Hilbert space enough that you cannot use this argument. So that's why we have to like directly use like representation theory to prove the anti-concentration. I skip other results, and then yeah, that's the end of the talk.
Any questions from audience?
Yeah, it can be anything.
So I think the topic that's the name of the topic, fermion linear optic, is really interesting. I mean, when talking about optics, we always think about photon, which is
right.
boson.
Yeah, this
so,
is.
So I don't know how are they related.
Oh yeah, this is definitely, yeah, this is the wrong naming. It's a misnomer. Actually, I don't remember. I tried to check on Wikipedia too, but my guess is that is linear because this is a linear transformation on the fermionic operators, I believe, but I'm not sure because sometimes for bosons, people think of squeezing as nonlinear, but I think squeezing is still a linear transformation on this. So I'm not sure exactly, but yeah, I think it's definitely from analogy to bosons. Yeah. Yeah, but it's an oxymoron. There is no fermion optics. Thanks.
Any other? So I think we can end our seminar today. So let's thank our speakers again.